So in this video, I want to talk about the cohomology spectral sequence for filtration. And this will be analogous to what we did last time, though we'll do it slightly differently, just to change things up. So what did we do last time? Well, we were looking at some filtration of some space. So I'll just call that a filtered space. And what we did is we sewed together a bunch of long exact sequences in homology. And then we basically called that sewed together thing an unraveled exact couple. And chased some elements around in it and saw that that gave us a spectral sequence, well, roughly. So for cohomology, we could do the same thing. Or, and what I'm going to do instead is look at filtering a DGA, namely the cochain complex, maybe cellular or singular cochain complex, depending on the situation. Now, I just want to make sort of an aside about how these relate. So the first part is that our filtration of a space, well, it doesn't necessarily give us immediately a filtration on the chain complex. So either the chain complex for X or the cochain complex for X, whatever setting we're interested in. But if we look at each of these inclusions, xp minus 1 into xp, well, if that's a cellular inclusion, meaning xp is just built from attaching cells, well, then actually we can build our chain complex filtration. Maybe let's do cochain complex for the current setting. So we could start with the cochain complex and x minus 1. Okay, that's just the 0 cochain complex. And then we'll include that into whatever cochain complex we need for attaching some cells. And then from that, attach some more cells and do the obvious thing to the chain complex, and so on. And so that'll give us a filtration of a cochain complex for X. Okay, so in a sense, this filtration of a space, as long as it's a nice filtration, could give us a filtration of our cochain complex. And the other thing is that above I said that we have a DGA, and that's true, but for now, we don't really need the algebra structure. What we're going to do is build up a spectral sequence. And if we did incorporate the algebra structure, then we just get a spectral sequence of algebras, and it would play nicely with that algebra structure, but we'll come back to that later on. So for now, we just need a differential graded module, or DGM. So differential graded module, and that's just a fancy way of saying a chain complex, or in our case, cochain complex, I suppose, but that's just a matter of indexing. Okay, so what we're going to really need to work with is a filtered differential graded algebra, or for now, a filtered differential graded module. And what does that look like? Well, let's call it A. This satisfies a few properties. So one is that it's graded. So we've got a bunch of graded components, and it's the direct sum of those graded pieces. Another is that we should have a differential. So there exists a map. This is a map of R modules, whatever category we're in, from A back to itself. and this will be degree plus or minus 1, whether we're in the homological or cohomological setting. And I want it to be a differential in the sense that it squares to 0. So really, in these first two, I've just defined a DGM. And then the filtered part is that we should have a filtration. And we just want it to be a nice filtration, so it respects our differential. That is, and I'm going to spell this out a little bit more precisely, though you can probably imagine what I mean. So there are two different kinds of filtrations, really, again, just depending on our indexing choices, but it's common in this world to use a decreasing filtration sometimes, or an increasing filtration. You can probably guess what that means, but let me write it out really explicitly. So I've got some FP plus 1A, my filtered component that lives inside FPA, and so on, and all includes to A. Or I've got an increasing filtration that I'm just going to index the other way. So here FP would include into FP plus 1. Okay, and this should be such that, well, the filtration is supposed to respect the differential, so if I just look at some filtered piece, FPA, then my differential should restrict to that. Well, when I restrict my differential to that, I should land back in that. Okay, so what does this give us? Well, this tells us that when we look at the homology of this complex with respect to the differential, meaning you just take the kernel of D mod the image of D. That got a little funky. Well, this is going to inherit the filtration. And so we've also filtered our homology, and I'm often going to be lazy and just write H of A here because I think of my A as coming with a differential, so why write it separately? And maybe it's worth saying that we usually use the increasing filtration for homology and the decreasing filtration for cohomology. So when you're reading in the literature about these things, then you'll often see that convention. Okay, so we've got this filtered differential graded module, and the whole point of this is to get a spectral sequence. So let's let A comma D, or I think of just A, be a differential graded module. And I just want to specify that our differential goes up in degree. So I'm thinking about the cohomological case. Okay, and along with that, let's take a filtration. And as I said, as is the convention, we'll make it a decreasing filtration. Okay. And then the claim is that there's a cohomological spectral sequence associated to this filtration. And what does that look like? Well, on the E1 page, we're going to see the homology of the filtration quotients. So HP plus Q of FPA mod FP plus 1A, right? And here I can quotient by FP plus 1A because I'm using that decreasing filtration. And sorry, I missed a word, so let me throw in here that I want this to be a bounded filtration. And that's so that I can talk about the convergence. I can always have a spectral sequence with E1 page given by these homologies of the filtration quotients, and then I can cook up the E2 page by taking the homology of that and so on. But if I want to know what this is giving me, well, then I need some kind of convergence. And so when we have a bounded decreasing filtration, this will converge to HP plus Q of A. So just the homology of A. Okay, and maybe a couple words about this. So now we've switched back to cohomological spectral sequence. Okay, so remember that our differentials go to the right and down now. And what do I mean by a bounded filtration? Well, we'll actually usually have even a better situation than this, but the claim is to get some nice kind of convergence that we should have for each n, that there exists an S and a T, so that really we end up with a finite filtration for the degree n stuff. So it's going to look like 0 sits inside our S-th filtration. Wow, that's really hard to say. And then the S minus 1, and so on, right? This is the decreasing filtration. And then it ends at some point with some FT. So the Tth filtration is just actually the AN. Okay, and this S and T could vary depending on N. So, okay, I don't want to worry too much about that for the moment. We'll have to deal with that later, but sort of a quick word about convergence. Remember that a spectral sequence converges just means that we end up really with an associated graded of the thing on the right-hand side. So we should get some associated graded for the homology of A. And what does that look like? Well, the claim is that we can come up with these E infinity things, where the p qth spot is actually just isomorphic to the filtration quotients of the homology. So remember, our filtration gives rise to a filtration on homology, and so we can take these filtration quotients for the homology as well. Okay, and so these are those associated graded pieces, and then there's some work to do to even try to cook up the homology or the cohomology of A. Okay, so I know that we haven't really addressed convergence yet. I'm kind of just giving some lip service to it as something that we will have to deal with soon. But let me say, at least for now, a little bit about what that means in this context. So maybe let me leave just part of that visible. Let's say we're looking at a first quadrant spectral sequence. And we're still in the cohomological case. So a first quadrant cohomological spectral sequence. Then the idea is that if we look at the E infinity page, and well, we should see these filtration quotients of the homology, of some filtration for the homology of A. And so in particular, if we're in a first quadrant situation, then we get a nice filtration. So the n plus first filtration of the nth homology of A will just be 0. Okay, and it's not that I'm filtering by homology degree, so I want to filter Hn in particular. And so the n plus first filtration will be 0, but then I'll have the nth filtration sits, that sits inside the nth filtration, which sits inside, and so on up until F1 of the nth homology, cohomology, and then F0 is actually the thing that I'm after, so that's going to be Hn of A. Okay, so as usual, I'm going to stick with our grading convention and let n be p plus q. And so what does that look like here? Well, on this E infinity page, what I've really got is E infinity, sorry, I skipped ahead. Let me hold off on that. So what I want to say is that I have this filtration of the nth homology, and now I haven't told you why that's the case. We'll have to see when we start to talk about convergence, but this is what the claim is making, is that there's some nice filtration of this homology, and when I look at those filtration quotients, well, really this Fn plus 1 Hn includes into Fn Hn quotients to Fn mod Fn plus 1. All right, that one's kind of silly because I'm quotienting out by 0. And I've gotten lazier. I'm not writing Hn of A everywhere. But I just mean that there's a little short exact sequence here. And I keep going. I've got a bunch of filtration quotients. So here it would look like Fn F1 mod the previous thing, F2. The last one looks like F0 mod F1. And so the claim is that these are terms on our E infinity page. So here, just looking at these degrees and calculating a little bit, I should get that this is n comma 0. And maybe let me say this continues. Here we've got the E infinity term for 1 comma n minus 1. And here we've got the E infinity term for 0 comma n. And so this gets at something that we were talking about in the discussion, which is that when I look at this page, down on the p-axis is where I see that E infinity n comma 0. And up on the q-axis is where I see, oops, can't write infinity, okay, E infinity 0 n, okay, and so really all along this diagonal, I'm getting a bunch of associated graded pieces to the nth cohomology of my complex, or my DGM. So all of these pieces together should build the homology. And so that's what we mean by this converges to this thing, and that there's some filtration. And this is what the filtration will look like in the first quadrant case. And now that doesn't quite tell us about the homology of A, because there are lots of extension problems, as we've said. So for example, just even taking some low dimension, if I look at E infinity 1, 0, well, that should include into the first homology of A and quotient to the term that I see E infinity 0, 1, this limiting term in this spectral sequence. And so I get this short exact sequence, but the thing that I'm after is really an extension problem of these two modules. So the short exact sequence may or may not be split. What I often hope for is that it does split, and so I can just say, okay, I have the direct sum of these two pieces. I've now found H1 of A if I can find the E infinity page of my spectral sequence. But in general, there could be quite complicated extension problems, and we've even seen that if you have Z and Z mod 2 on either end, then it could be the direct sum, or it could just be Z in the middle. So, okay, again, we still need to address convergence more deeply, but I'm kind of building up to that and trying to explain what I mean. And we had this question in discussion about looking at these diagonals and how do we figure out how these associated graded pieces fit together. And I sort of want to say we should go from the bottom to the top. It's not really an arrow, so maybe I'll just draw it as a dotted arrow or a dashed arrow, but this En comma 0, this is sort of our smallest piece. And in fact, we know that that sits inside our module. The question is, how do we build it up from there using the associated graded pieces as we go along the diagonal towards the q-axis? Okay, let me stop there and investigate this a little bit more deeply in the next video.